First thing we're going to do is talk about the derivative of a function. The derivative, which is also known as a variety of different things, instantaneous rate of change, the slope as the slope of the curve at a point P, or as we've learned, the slope of the tangent line of some particular curve. We can define this or use a lot of different notation. So f of x, or I'm sorry, f prime of x, so that defines the definition of the derivative. We can also call it dy dx. We can call it y prime. We can call it df dx, or we can call it the derivative with respect to x of the function f of x. Excuse me. So all of these are possible ways of writing it. F prime of x, dy dx, y prime, df dx, or d over dx, which is the derivative with respect to x, of the function f of x. Next, let's talk about what the definitions of all of these things are, and you know these already. F prime of x is the limit as h approaches 0 of f of x plus h minus f of x all over h. You can define the definition of the derivative at a point to be the limit as h approaches 0 of f of a plus h minus f of a over h, which is just substituting a, or some point, in for x. And then we also have the other way to say the definition of the derivative at a point, which is the limit as x approaches a of f of x minus f of a over x minus a. So all those are things that you either should already know, or it's just notation, the stuff that we wrote in black. So that's not too difficult. Now we're going to do a problem here in 3 different ways. So given this function, the square root of x, find f prime of x at x equals a. Use f prime equals the first limit definition of the derivative that we had. So the limit as h approaches 0 of, I don't need to write f, I can actually just use the function here, square root of x plus h minus square root of x all over h. So probably the easiest way to do that is to rationalize the numerator. So I'm going to multiply the top and bottom by the square root of x plus h plus square root of x. So we're going to end up with, if I multiply the top out, I get x plus h minus x, and the denominator is h times square root of x plus h plus square root of x. So the numerator becomes h, and the denominator becomes h times square root of x plus h plus square root of x. The h's cancel, and now I can do a straight substitution of h equals 0 in, and I get 1 over 2 square root of x. So this is f prime of x. Now, it tells us to find f prime of x at a, so I would simply substitute in a, and I would get f prime of a equals 1 over 2 times the square root of a. Now let's see if that works in the other ways that we do the definition. So the limit as h approaches 0 of the square root of a plus h minus the square root of a all over h. I'm not going to spend the video time doing this, but you can clearly see that it will be identical to what we did in the previous problem, except x has been replaced by a everywhere. So what we're going to get when we're done is f prime of a equals 1 over 2 root a. Now let's look at the third problem. We're going to use the definition of the derivative at a point with f of x minus f of a over x minus a. So the limit as x approaches a of square root of x minus square root of a over x minus a. What we would do here is we would probably rationalize the numerator, or you can factor the denominator into square root parts. I'll do that this time. So square root of x minus square root of a over square root of x minus square root of a times square root of x plus square root of a. Don't forget that limit sign in there, Jason. So we will then cancel these off. We will get the limit as x approaches a, 1 over root x plus root a. When I substitute a in for x, because now I can directly substitute, I will get 1 over root a plus root a, which is 1 over 2 root a. So the derivative at a is clearly 1 over 2 times the square root of a. What we're going to do now is we're going to graph both f prime of x and f of x on the same graph. So if f of x equals square root of x, that means the derivative is going to be 1 over 2 square root of x. So I'm just going to show you what it looks like on the graphing calculator. So the blue one represents the square root of x, and the red one represents 1 divided by 2 times the square root of x. Now, if you're typing this in your calculator and you're not getting 1 over 2 divided by 1 over 2 root x as the red one with what you're getting, you're probably not typing it in right. So just make sure that you put the entire denominator in parentheses when you're typing it in, or you use the division sign where it actually you can see the top and bottom. One other thing I wanted to point out is that on your graphing calculators, you can actually use a derivative function, and that can kind of help you. So what I did, I didn't type in 1 over 2 root x, but I could have. But I typed in something where I can actually put the derivative in. So I'll show you guys that in a minute. So see that clearly the red one and the black one are identical. So I just kind of wanted to show you that. If you want to type in taking the derivative of something, and notice that I took the derivative with respect to x, and then in order to graph it, I said it was at x equals every single value of x. If you wanted to get a numerical value, you could have typed it in otherwise. But what I would do is I would go to the math function, and then if you get to number 8, and it's the function's called nderive, that gives you a numerical derivative at a point. So I type that in, and then it actually graphs it if you make the point x, because then every single point it's calculating where the derivative is. So very briefly, that is graphing those things. Notice that the graph of the derivative was always the slope of the tangent line of the function. So if you look at the graph, what we can see is, for example, just take at 2. If you take at the value 2, if you kind of look at what the slope is here, the slope of this is probably a little bit less than 1. And what you notice is that the slope is continually decreasing, but is always positive. And so if you look at the black curve, the slope is always positive, but it's continually decreasing, and the slope is getting smaller and smaller as we move along. Okay, so that is what's going on with the relationship of the function and its derivative. As you graph the function, you can see the slope of the tangent line consistently. And then you end up graphing that. All right, so what I'm going to do is on the back of your worksheet, I'm going to give you about however long you need, press pause, and then you can go over, see if you can figure out which derivative graph matches with the function graph that's on the left. So derivative graphs are on the right, function graphs are on the left. I'm going to pause for about 6 seconds or so. You pause the video and then do the problems, and then I will go over them with you. Okay, the first problem, the answer is E. Second problem, the answer is C. Third problem, the answer is A. Fourth problem, the answer is B. And fifth problem, the answer is D. And I'm going to show you all of those on Desmos just to make sure that you know why each of these is true. And then after that, we will be done. So if we look at the first graph and its derivative, that clearly matches up with E. Also notice how the slopes are going. So the slopes are real small, and then near the end, the slope starts to get a whole lot bigger, but all of the slopes are negative. So that's why the graph of the derivative is always below zero. If you look at the second graph, that matches up with letter C when it's got a derivative. The slopes of the entire first part are always negative, and then the slopes of the entire second part are always positive. And as you get closer to the asymptote, the slopes get either more and more negative or more and more positive. If you look at the third one, this matches up with A quite nicely. Notice that these slopes are positive, and the slopes are positive and decreasing. And then once you get to here, the slopes become negative and become more negative, more negative, more negative, until you get to a certain point when the slope starts to kind of level off. And then once you get to here, the slope is increasing and positive repeatedly. If you look at the fourth graph, that matches up with letter B quite nicely. So this is the graph that we had. The slopes are very, very, very positive over here. The slopes are always positive, but they continually get smaller and smaller as we go along. Finally, we have this function that kind of looks like an exponential. The graph of its derivative is very, very, very close to it. We'll talk about why that is when we get into derivative rules. But one thing I do want you to notice is that there is one exponential function where the derivative actually is exactly the same as the original function, and that is the exponential function e to the x. So e has a lot of pretty cool properties that you need to be aware of. Hopefully you enjoyed this video.